Everybody. My name is Rudy Shankar. I'm the director of the Energy Systems Engineering program here at Lehigh University, and welcome to our ESE seminar series. This is the sixth in the spring for the spring session, and we have an excellent topic which kind of follows up on what you heard last week on the practical realities of energy transition. We have Michael Caravaggio, who talked about the global state of energy transition. You know, what you heard last week from Stan, where there's some key points that, in the enthusiasm, the exuberance, when people looked at renewable energy and clean green energy as to what some of the problems could be, Stan kind of alerted us as to what some of the practical issues are. And there are many, and some were very much anticipated. The main one being that you have to use all the tools in your toolkit, not just the ones that are designated to be clean and green. Also, you mentioned that you learn by doing. Lessons learned is really important. And that the energy industry impacts everything else that we do to address climate change. So we have a bigger responsibility, which also is maybe more difficult, but it is a bigger responsibility. So we leverage solutions just beyond the electric power sector. And the fifth practical reality that Stan introduced was there's no one size that fits all solution. And that was kind of validated before and been validated since we've gotten into energy transition. So Michael's talk is going to look at this global state of energy transition. And Michael will use pictures to convey some very important results. It's fun kind of following him on LinkedIn. And I tell you, if you're not following Michael, please do, because his graphs and his commentaries are just gems. So having said that, Michael is the Vice President of Energy Supply at EPRI, and I'm getting my glasses, sorry. And conducts research on all aspects of electricity generation for a global group of generating companies. The sector has collaborative R&D programs covering the thermal, renewable, and next generation fleet management and operations, digitalization, materials, thermal optimization and emission controls, air quality and health, water and land management. Give this guy some more responsibilities here. Before joining EPRI in 2014, Mike ran the Integrated Chemistry Solutions Limited, a Singapore-based business development and technical consultancy serving the power and water industries. Early in his career, he held various roles, including engineering, supervisory, and management with Ontario Power Generation, a Canadian-based utility company. Mike received a Bachelor of Science degree in environmental engineering from the University of Waterloo and an MBA from the Nanyang Business School at Singapore. Welcome, Michael. The floor is yours.
All right. Thank you very much, Rudy. Thank you, everyone, for joining. Hopefully this ends up being fun. So we're going to cover the global state of the energy transition. That's pretty much maybe a bit of a misnomer. I'm going to focus on electricity, but us electricity guys and gals, we tend to think that we're really the cornerstone of energy. So that'll be the focus. I'm part of the Electric Power Research Institute. As was shared, I'm in the generation sector. You scan that QR code, you can see our research portfolio and get some details on that. This is going to be a data-driven PowerPoint set. So we're going to look at a lot of data. I will share the slides with Rudy to share with the class afterwards. And there's a lot of slides, so we'll see how it all goes. But first off, want to call back to my friend Stan. So my friend and colleague Stan Rosinski did do a seminar just a little over a week ago. Please go back to that. He talked about the energy transition and some global trends. I'm going to go a little bit deeper on all that. So what's the agenda? I'm going to do a little on EPRI, just to level set who we are and why we have something to say here. I'm going to talk a little on the electricity energy supply. I'm going to talk about the world, some ideas on the path forward. I'm going to give you my punchline near the beginning, and then try to prove my case through the examples along the way. So we'll look at the US, we'll look at energy or electricity at different time scales, because that's critically important. We'll look at CAISO, for those who don't know the acronyms. In the acronym soup, that is the electricity industry. That's the California Independent System Operator. Then we'll look at Europe. Europe is very much like the US and the rest of the world. So there'll be some similarities between what we're seeing and what they're seeing. We'll do some back and forth to drive home some points on the ideas on the path forward, and then we'll open up for some summary and discussion. So hopefully that sounds good. Hopefully everybody's excited and ready to have a good time. So I don't know if there's emojis in Zoom, but if there is, I'd love to see them. All right, so what is EPRI? We call ourselves a leading global collaborative energy R&D firm. We're actually a not-for-profit based here in the US, but we have a global membership. We're doing about $450 million a year in annual collaborative research across 45 countries. And we're basically touching into every power company around the world, or a good share of them, and as well as the OEMs, so the original equipment manufacturers, and other participants in the industry. And what we're trying to do along that journey is basically deliver solutions that make our electricity supply safer, more reliable, more affordable, and more environmentally responsible. So we're driving on that through a global collaboration. And like I said, we are not for profit. So it's more of a look at trying to do things independently and objectively so we can get the right solutions into power companies so we can achieve on those aims. When we talk the future of energy, or we talk the energy transition, there's a big forcing function: decarbonization. And decarbonization is critically important, and over different time scales, what the technologies we need to bring to bear to achieve that are changing. In the meantime, we have an electricity supply that needs to remain reliable, affordable, and stable for the folks that rely on that system, which is everyone, right? So I think I often have heard that when you think about the electricity sector, it's not a big portion of the GDP, but it's often referred to as like the first, maybe 5% of GDP, because once we don't have electricity, really the rest of the sectors pretty much fall away. So it's sort of basically everyone believes when they hit that light switch, the light's going to come on. That's not necessarily a guarantee. There's a lot of moving parts and a lot of things that are required to make that happen. And we're seeing some of that. So we've got the decarbonization that's bringing in new technologies, but we're having challenges with resilience and transforming the system. So making energy more clean, affordable, and reliable as we go through this transition is not simple. And EPRI goes into a lot of work on this. So these just in our generation portfolio, some of the R&D programs that we look at to understand this. These are deep dives on very technical topics. And each one of these is a global collaboration where there may be 20 or 30 or 40 or 50 companies from around the world looking at issues on, say, generators, or on selective catalytic reduction performance issues, or on wind energy. To understand that, bring together a global stakeholders, subject matter experts to solve issues. When we talk about these programs, they're actually huge resources. They've been in existence for 30 or 40 years in some cases. There are libraries of technical webcasts, decades of user group and interest group and working group content, detailed technical reports, and then the ability to launch new research. Because as we go through the energy transition, it takes a huge amount of effort and knowledge to keep that system reliable and affordable. And when we look at EPRI, this is who we really are. We can touch into a number of countries. We have 170 technical experts just on energy supply, just looking at the issues that I'm going to be talking to you about. So that's EPRI. Let's get into the meat of this presentation. So let's look at the global state. Where are we at? And I apologize, this is 2023. It's not quite updated for 2024, but this is the electricity supply. This is the global electricity supply. I think sometimes we focus on the European experience and the North American experience, but you should look at the Asia. Asia requires more electricity than both Europe and North America combined. And so when we talk about a global energy transition, you can't ignore the fact that Asia exists and that Asia is primarily coal driven. And although you see lots of news articles about China adding more wind and solar than the rest of the world, that is very much true, but it is still a coal-driven economy. And so solutions that decarbonize coal are part of that overall necessity for us to actually achieve energy transition. So you look at the color code here, black is coal, red is wind, yellow is solar. And you can see where we're at in 2023. We want to actually look at the progress of our energy, and this is energy, so this is terawatt hours. This isn't gigawatts or terawatts. These are terawatt hours. So this is how we measure how much benefit we got out of an energy source, not the size of that power plant. Power plants don't have that hour aspect. They just have the capacity, and we'll go into more detail on that. But this is the last 10 plus years. You can see coal was the primary source back in 2012. It's still the primary source. If you look at the lower two graphs, we've got year over year. So that's the change year over year, and not surprising, we see the energy from solar and wind increasing pretty much every year over year. We see coal sometimes go up, sometimes go down. We see gas generally increasing year over year, except for the pandemic year where you see in 2020, both coal, gas, nuclear, and oil all dropped. And on the right of that, we see the cumulative over this whole 11 years, this whole transition period. And we see, I think what we all hear about, the solar and wind are producing a lot more energy than they used to. And they've produced, in the case of wind, almost 2,000 terawatt hours more than they did in 2012. Solar is significantly up, but coal and gas are also up. So in North America, we've done a switch from coal to gas. And in Asia, in addition to building a lot of renewables, we're building a lot of coal. So the transition is going to involve all these technologies. We need to figure out how to decarbonize all of it. So let's acknowledge, though, that we haven't had a perfectly smooth run here. We've had some challenges. So the blues are maybe energy challenges or rolling outages. The reds are countrywide blackouts. So we've had some bumps in the last 6 or 7 years, and we continue to have risk for these bumps. And we're going to talk about why some of that happens as we go further into this presentation. But I'm going to get right to my punchline. What we need. We need generation technologies that are flexible to match with what is increasingly being built out, which is a lot of solar and a lot of wind. As we build more of that out, we can have a lot of that at one time, but then the sun sets or the wind dies down and it drops down. So what we need to match that up needs to be very flexible. And if you think about operating things flexibly, you can think how that can be maybe more wear and tear, more challenging, and especially when you think that when we think about an electricity supply, it took decades to build. So we built a lot of power plants that were baseload or steady state operation was the original design intent. But as we add more variable resources like wind and solar, we need to flex them a lot more. In addition to that, a big thing of what we need is we're going to end up having a ton of capacity. We're going to have lots and lots and lots and lots of gigawatts producing maybe a similar amount, maybe a little bit more of gigawatt hours, but we're going to have a lot of capacity to match everything up, because as we build solar in the summer here in North America, maybe a 25% capacity factor. You get the gigawatt hours out 25% of the time of the total installed capacity in theory over that 24-hour period, because the sun's not up or it's up only part of the sky. So you don't have necessarily those gigawatts for every hour of every day. So I need someone else to fill that in. So I need gigawatts of other things to match that up. And that's the summer. You think about the winter, we even have less solar, so that's more of a challenge. Because we're going to have all this capacity, operating costs might not necessarily be really the driver, because when we really need energy, we're going to pay anything we can to get it. All those situations when we had the blackouts and the other situations, folks would have paid anything to keep that system up because their economy shut down when they had the blackout. So the GDP cost of those blackouts far exceeds anything else. And our markets are not perfectly set up for this. So if we're really talking about achieving zero, we need stuff to match up with our solar and wind, which are good low carbon resources, but can't produce all the time. And that's where the 6 solutions on the right here. 2 of them are well proven, conventional nuclear and of course hydro, but we have trouble building more of those. The other 4 are things that our EPRI are looking at today. So CCS and around the world, we're looking at it. That's a proven technology, carbon capture and sequestration. It can take my dispatchable thermal plant and make it lower carbon, so I still can match solar and wind and achieve decarbonization, and achieve decarbonization at the same time. Not scaling yet. Small modular reactors, I think people have heard about these, is basically to reduce the cost of building out new nuclear. Again, not quite scaling yet. We may have some solutions in the form of lowering our carbon, the fuel in our carbon, so things like hydrogen, or maybe renewable fuels, or long duration energy storage may be part of it. In the meantime, though, because none of these are scaling to actually achieve decarbonization, we need to keep our dispatchable fleet viable to ensure that we continue to deliver reliability and affordability. So I've gone to the punchline. Now I'm going to walk you through why this is the case. So let's start with the US. And start first with the gigawatts, not the gigawatt hours. So these are our gigawatts. This is our installed capacity. Every year since 1950, at the bottom there, this is what we've installed that's still operating. In the top left is the total capacity by different technologies and the average age of those assets. So you can see the new stuff is wind and solar and battery, but we still have a lot of gas in the system. So the combined cycle fleet and the combustion turbines are about 20, 25 years old. Still have a lot of nuclear. The nuclear is getting long in the tooth. It was built on average in 82. Still have a lot of coal getting long in the tooth. It was built on average in 77. And still our hydro fleet is actually the oldest of these fleets. All these gigawatts are not the same, right? So a gigawatt of nuclear and coal and gas, I can get more gigawatt hours out of them by putting more fuel to them. For solar and wind, that's not the case, right? I have the wind and I have the solar when I have it, and then I don't. Storage can address some of that by moving things around through time, but storage doesn't provide any real energy. It's just taking energy from one time and putting it to another time, perhaps when it's of greater value. So that's the gigawatts. We look at the US in terms of our gigawatt hours or terawatt hours. This is the transition. So we were significantly dependent on coal about 15 years ago. That has tailed away. It has largely been replaced by gas. We do have solar and wind scaling, but they aren't the main driver for that offset on coal. It was predominantly through gas. Wind and solar are adding contributions to that. But because of their variability, the notion that they could be a full replacement, I think, is not the case. And I'm going to present some data on why that is. So we've talked about gigawatts. We've talked about gigawatt hours. This is just batching. It's not perfectly correct, but batching generation technologies by how they operate. So on the right, we've got things that are dispatchable. I need more energy. I can get more energy out of it. I need less energy. I just turn them down or turn down my fuel. that's my dispatchable assets. In the middle are semi-dispatchable. So hydroelectric plant is very dispatchable, but if I don't have water, I can't use it, so it's not necessarily done that way. Nuclear, we tend to run those at full load all the time, although in France and in other regions, they can be more dispatchable. And then, of course, wind and solar. When they're available, less energy, but we can't make them be available every moment that we need them, right? And so electricity demand fluctuates with throughout the day, and we need to have power when people are looking for using that power. So let's put the terawatt hours and the gigawatts, or the gigawatt hours and the gigawatts back into this. So in the blue, we've got how much of this stuff we have in 2023 for the dispatchable power plant, the semi-dispatchable power plant, and the variable power plants. And we can look at some difference in how much energy we get from each of them. So if you look at nuclear, we have 101 gigawatts of capacity. It provided almost 20% of our total energy. But if you look at wind, 148 gigawatts of capacity, that's a lot more capacity, but it only provided 10% of the annual energy. And that has to do with the fact that wind's not always blowing. And so we can build a lot of gigawatts, but it doesn't necessarily cover our needs. And our needs are really, for 2023, that number in the top right corner is the key number. That was the highest amount of gigawatts we needed in the US for a single hour. So between that 820 of dispatchable, 218 gigawatts of semi-dispatchable, and 237 gigawatts of variable, which is 1,200 megawatts, the hardest hour was that 742 gigawatts to make up. If I have something dispatchable or semi-dispatchable, I might not need as much to get to that 742. For variable, there's an odds there, right? Is that 742 going to line up when I have a lot of solar? Is it going to line up when I have a lot of wind? Not always the case. So if we look at the different seasons of 2023, we can look at when we really have challenges getting or meeting the electricity demand and when we don't. So winter days and summer days are the hardest, and summer is much harder in the US than winter. And the spring and the fall are a lot less difficult to cover. But this is the hourly, right? So you got the hour on the marginal day, the resource makeup for that. And you can see, so the green is nuclear, yellow is solar, red is wind, blue is water or hydro, black is coal, and light brown is gas. You can see what's flexing. When we need a lot more electricity, we can't force more solar to be on. We can't force it to be more windy. We're reliant on gas and coal. Today, that gas and coal is not decarbonized. In the future, we need something that is decarbonized to cover these margins. And it's massive, right? It's a massive difference in terms of what we need in terms of electricity on a summer day versus a spring day. And so now we're getting into some of the meat of these resources, because I can burn more coal or burn more gas on a summer day or on a winter day. But my other resources, what I'm building today, like solar and wind, they don't operate like that, right? So this was our annual energy or monthly energy need in electricity across the resources for 2024. We need a lot more in the summer, a lot more in the winter, a lot less in the spring. So this doesn't necessarily tell you much, but if we pull it out, so we pull all the resources out, we can see, okay, we burnt a lot more gas in the summer and in the winter. We burnt more coal in the winter and in the summer. Well, let's focus on what we're building. We're building wind, we're building solar. Wind dies down in the summer in the US. Different continents and different regions, it'll behave a little bit differently, but generally when temperatures get hot on a continent, air rises instead of blowing across the continent, we get less terawatt hours. We have an energy deficit if we were trying to rely on wind resources to cover my my summer need. You can see I got a lot of extra wind in the spring, not necessarily a time where I need a lot of electricity. Solar is much better matching for summer, but then you look at the tails, you look at the winter, and I can build a lot of solar to try to hit a summer need and not necessarily cover my winter need. Especially if you remember that we do have winter peaking basically in the evening as the sun's setting and in the morning before the sun is risen. So let's take this a little bit further and understand a little bit more about the difference between those gigawatts of solar and wind that we're building and what they may produce for us on a terawatt hour or megawatt hour basis in any given month. So let's spend a little bit of time on this. So this is US wind and solar. Capacity is the top line every month since 2019, so building up. So we went from about 125 gigawatts to now 275 gigawatts in the last month, which was December of 2024. The three lines below are the hourly average generation from that combined wind and solar, the min hour in that month from the wind and solar, and the max hour. You can immediately see I'm building gigawatts of this stuff, but I'm across the continent, I'm not getting the 125 gigawatts on any hour in any month back in January 2019, and we go to fast forward to December 2024, and we're still below 150 gigawatts on the best hour. The average hour is about 75 gigawatts from that 275 gigawatts of capacity now, and the min is a lot less than that. Those min hours are critically important because electricity supply must be balanced every second, 60 times at 60 hertz here in the US, 50 hertz in Europe. We need power every minute. When we don't, we go back to the earlier example of those red areas where we can have blackouts, or the blue areas where we have some significant cost pressure and challenges. So let's walk through in a little bit more detail the difference of some gigawatts by different types of resources for a particular region. We'll use CAISO, and I've got a whole bunch of words here so you can read through it later. This was one of the posts that I had done, but let's focus on the left here. So the top is the installed gigawatt capacity for California ISO in 2024. And you can see the different technologies. You've got batteries, you've got a natural gas combined cycle, you've got combustion turbines, you've got a lot of solar photovoltaic. So that's the power plant. That's what they've built in terms of power plant. Next layer down. This is the benefit they've gotten. This is the amount of annual energy in the left. So that's how much energy I got for all that power plant. And then on the right in the middle is the peak reduction. What do I mean by that? So 48 gigawatts was the hardest hour to make everything work in California in that year, 2024. For that 22 gigawatts of solar that we had, it reduced that peak. If I take the peak and I reduce the solar for every hour of every year of the entire year, the peak goes from 48 to 46. So that solar didn't really reduce my need for having to have other resources present to cover that load. If I add in the batteries, solar plus batteries, it does much better, drops it down to 40. But if we look at nuclear, we only have about 2 gigawatts of nuclear in California. It dropped the peak demand from 48 to 46. So a gigawatt was a gigawatt. So let's normalize this. And that's what the bottom does. So this is basically, I built this power plant. How much benefit am I getting from this power plant? So if you look at the solar and the nuclear example, so if I build a gigawatt of solar in California in 2024, I got 2,000 gigawatt hours for each gigawatt of solar I built. For nuclear, I got nearly 7,000 gigawatts. That's the difference in the capacity factor. Nuclear can run 100% of the time, or nearly 100% of the time. Solar runs when I have the sun shining. That's one aspect of the benefit. The second, probably more important, is this backup power plant. That peak reduction. How many gigawatts less did I need of another resource based on that reduction in that hardest hour to meet did I get for each gigawatt I installed of the solar and the nuclear? And you can see nuclear is nearly 1 for 1. Install a gigawatt of nuclear, I don't need to have a gigawatt of coal to back it up. I don't need to have a gigawatt of gas. is done. For solar, I'm getting less than 0.1 gigawatt reduction. Not great. So I add in the batteries and I do a lot better. So that's the battery plus the solar gigawatts. Now I'm getting 0.2 reduction, but batteries consume energy. I can't freely move energy from the middle of the day to the evening peak without losing some energy. There's round trip efficiency. And so that we see that in the annual energies. The gigawatt hour per gigawatt installed then drops. This drives costs, right? Because I get partial solutions. And a partial solution can lead to, I need to put in something else then, and something else, and something else, and that can increase costs. And so let's take a look at where we are in the US in terms of costs. So these are retail rates. These are important because this is ultimately what people are paying for that electricity. You can see things on wholesale rates and things like that, but ultimately most see the retail rates. And we've got the residential and the industrial here. And you can see our top states. So Hawaii, not surprising. It's difficult to serve electricity on an island nation or an island state. So it's the highest. But in the continental, California leads the way. And so that's the residential on the left, industrial on the right. The year-over-year increase or decrease in some cases. So I've got the top 10 in blue and the bottom 10 in gray there. You can see some regions. I'm going to pick on California here again. Even though it's at the top of the list, it's also increasing at one of the higher residential rates or residential for the residential rates. And it's number 2 for the year-over-year increase in 2024 to 2023 for industrial rates. So that's where the rubber hits the road. And this is the accumulation of costs and some of the challenges. California also has a big wildfire risk, which drives some of that cost and adds some complexity. There's also the wholesale costs, right? So we have these markets and wholesale costs, and you can see 2020 to 2024 here for California. You can see a scatter chart there. I'm not going to dive into the scatter chart. Below it is basically the average for 2020 in the wholesale. Then 2021 is the orange one. The green one was 2022, etc. You can see it goes up and down, changes. But it doesn't change the fact that every year the retail rate is going up. So the retail rates are the gray bars. It's pretty, it's not controlled by that wholesale price. That wholesale price is optimizing an hourly dispatch or a 5-minute dispatch, trying to affect costs there. 2022 was because of the Ukraine crisis, because gas prices went way high. You can see that we've actually had a really high set of values here, not when the demand was the highest, but that was actually corresponding to December when gas prices were really high and they were setting the price. So these varying wholesale costs, though, didn't really do anything. The retail price went up, went up, went up. What's driving the retail price? Transmission, distribution costs. And this ties back to the other issue. So if I need more power plant to manage something, right? If I have a gigawatt that doesn't replace another gigawatt, then I need to have more transmission to go to that second backup power plant. And I need to receive a rate on that. Distribution is even a little bit more complex because when we look at our distribution costs, we used to just have electricity that was basically coming from central power plants to homes. Now we have it going both ways. Now we have bigger electricity needs at houses. So that can incur additional distribution costs. So looking at just the wholesale costs can be somewhat misleading when trying to understand the entirety of an energy transition. So it's really important. You can look at wholesale costs, but always look at the retail costs and go, well, what am I maybe missing in terms of this wholesale cost story if the retail prices continue to go up? because that's ultimately what people pay. So that was the US example. Let's do something similar, but in a little different fashion with Europe. All right, so this is the installed capacity in Europe, the bar charts or the column charts. The inset is that transition. So you can see Europe really has needed about 4,000 terawatt hours a year since about the late 80s. You can see how it's evolved. Right now, gas was the highest in 2023. I think that was nuclear second, coal up and down, and you can see similar as with the U.S., solar and wind are increasing. But if that's the energy, if you look at the installed capacity, solar is number one in Europe, 207 gigawatts. Onshore wind is number two, 195 gigawatts. Then we get to gas, which is 190 gigawatts. Then we get to nuclear. They also have about 18 gigawatts of offshore wind. So although they get more of their energy from nuclear and gas than they certainly do from solar and wind, the capacity, the power plant in terms of gigawatts was built up with a lot of variable resources. So we're going to do a heat map walkthrough this time. And what do I mean here? And I pulled this from Energy Charts, which is a great website for looking at information on the electricity system in Europe. But this is 24-hour period on the y-axis. The x-axis is 365 days of the year. And I've highlighted two numbers, the peak electricity load in 2023 for Europe and the minimum. The minimum is less important. Let's focus on the peak. So we had those hundreds, 200 gigawatts of wind, 200 gigawatts of solar, 200 gigawatts almost of gas, but really their peak hour is actually only 393 gigawatts. So it's not that big of a number. Let's see what this looked like if I take all the solar generation for the 2023 and subtract it from this and see how much that peak maybe drops. So the peak goes from being in January to now being in December. It went from 393 gigawatts to 391 gigawatts. It dropped by 2. 208 gigawatts of wind, of solar reduced the peak demand in Europe by 2 gigawatts. Why is that? It is a winter peaking electricity system. So you're not going to get a significant reduction in terms of that peak need from the installation of solar. So that's low-cost energy, certainly, but it doesn't replace the need for other power plant. And it does drive that other power plant to need to operate more flexibly because the sun comes up every day and goes down every day, which can drive up the cost on those other plants. So let's add in all the wind as well. So they had about 190 onshore and about 20 offshore. So now we have 400 gigawatts of wind and solar in the continental Europe. And it dropped that peak load now a little bit further, dropped it by 43 gigawatts. So it dropped it to 350, moved that peak hour to in the evening in January. So that's good. So by adding wind and solar together, we can do a little bit better than the solar did on its own. Now let's look at a counterfactual or a different example. Let's look at what nuclear did. Recall there was about 90 gigawatts of nuclear. So I'm going to wipe this all out, look at the total demand for every hour in 2023, and just take away the nuclear delivery for 2023, actual numbers. That 98 gigawatts reduced my need by almost 80 gigawatts. A significant difference, right? A gigawatt is not a gigawatt is not a gigawatt. And so if we run the numbers similar to like we did with California, not as good in terms of the continental Europe for the entire year of 2023. Basically a gigawatt of nuclear dropped the need for other capacity by 0.8. Solar did almost nothing because it's a winter peaking system, and those winter peaks tend to be in the evening or in the early morning, depending on how cold the night was. For wind and solar together, a little bit better, but it's only dropping it by 0.1 gigawatts for every gigawatt of installed capacity. So where are European costs going? And how are they faring on decarbonization? So let's take a look at the European nations. So this is 2020. This is 2023 on the right. What I have graphed here this time is the carbon intensity of their electricity system, so the gram CO2 equivalent per kilowatt hour. And then on the x-axis, it's the euro cents per kilowatt hour, right? So if you're in the top right, that's a really bad spot to be. You have high emissions for your electricity and it costs a lot of money. Nobody's in there in 2020. We had the challenges of the Ukraine war in 2022. So we transition. Lots of people's costs have gone up significantly, and not a lot of movement really on the CO2 intensity. We had 3 in the lowest cost, lowest emission in 2020. By 2023, we had 4. This is what they look like in terms of energy delivery. And what you'll notice is they tend to have a lot of hydro and a lot of nuclear, and some wind. They're not predominantly wind, they're not predominantly solar, and it's that challenge of trying to match variable resource with that 24/7 electricity demand that sort of is a barrier to necessarily seeing that. So a lot of hydro, very good. A lot of nuclear, we're doing very good in terms of the costs and the CO2 emissions when we look at Europe. Let's just zoom out a little. Let's look at the biggest countries. And we took the cost aspect off this time. Now we're looking at the energy mix for the year. So every year, every country has basically 100% of their supply made up by an energy mix. And they're put in order here of CO2 intensity. So where they're at, and I think this is 2023 data, these are big systems, not little systems like Costa Rica or Norway or something. These are 500 terawatt hours or bigger, major economies. You can see France is by far the leader, 56 grams of CO2 per kilowatt hour. It's done that largely through nuclear. You can see Brazil and Canada fall behind. They have a lot of hydro to them, but they're a lot more carbon intense than France is. You can see that as a ratioing on the right, where everyone's divided by the France carbon intensity. So Brazil is nearly twice, Canada is nearly 3 times. Let's focus a little bit on Germany, because they focused a lot on wind and solar to try to drive down carbon intensity. And they haven't achieved the same aim. And if you recall from the last slide, the costs have not been able to match what was achieved in France. So we've gone through an example of the US, we've gone through an example of the Europe. Now let's do a little bit of ping pong back and forth to drive home some thoughts here. So we talked about reliability on the world scale. If we look at North America, we have a company called the North American Electricity Reliability Corporation that's responsible for the reliability of our bulk energy or our electricity system. They look at reliability on the marginal days. So they do one for summer, they do one for winter, and they also look at long-term reliability. These used to all have gray regions. We used to not have reliability concerns in the system. That is not the case anymore. We have many regions in the orange, which is elevated, and some regions in the high, which is high risk. We also do something that we've never done or never used to do. We load shed occasionally. So we've had winter storms where we've actually had to load shed, which means black people out so that the system doesn't black out. Like we saw in the cases of Brazil and some in Chile and Cuba in that earlier slide. So that's a challenge, and that's an issue. So we're gonna look at some of the winter data for the US and see what it's telling us. So for this here, we're back at the hourly scale. This is a peak hour for winters for the last 10 years. So you can see we didn't have 2016, it wasn't that high of a peak hour. 2017, it wasn't that high. South Central cold weather event. So that we had rolling outages here. There was a NERC report written about it. Jan 2nd, 9 p.m. Eastern is when we ran into that issue. And that's when we had the highest peak there. See, nothing. Winter Storm Uri, one of our worst events ever. Actually wasn't that high of a winter peak for the continental US, but we still had issues. You can see Winter Storm Elliott. You can see actually 2025, this year was our highest winter peak ever. So we've really hardened our system because there was no rolling outages this winter. We delivered. Remember what we're building. We're building solar and we're building wind. This is what the energy mix looked like on those peak hours. You can see that as we've gone further and further, gas keeps going up, even though we're not building a lot of gas. Wind can go up, can go down. Last couple of winters have actually had windy periods during those highest demand, which has actually helped us not have an event there. Whereas you look at 2021, it was a really low wind event associated with that cold winter spell that led to the load shedding in Winter Storm Uri. So just to drive home the point of the difference in terms of when we look at our electricity mix and how it responds to that need for electricity on every hour, what do we have here? We don't have this in time series. It is January 2025, so that the far right is those highest peak hours in terms of total demand for the year. You can see gas and coal and hydro to a lesser extent. When we need more megawatts, we get more megawatts out of the resource. You can see nuclear is base loaded, so it just sits up at full load. You can see solar, the sun goes down every day. So unfortunately, we have some in the bottom right there where demand is really high and the output is low or near zero. And you can see that we had a good winter in that it was windy when it was really cold. There's nothing that guarantees that's going to happen. So sometimes people say it's better to be lucky than good. So there's some luck associated with that. We have hardened our systems so that they can perform better, but it's been windy the last couple of winters when it's been really cold, and that's helped us. So we looked at the hourly. Now let's look at the day. How much energy we need in each one of these days to the hardest days in the winter to fill everything up. And again, you can see, all right, so these are the megawatt hours for the entire day, not the hardest hour, but the entire day. How much energy did I need? You can see it's again continuing to climb up in 2025. You can see that, yes, we're getting more every year when it gets higher out of our gas fleet. Some years in coal goes up, although we're shutting down coal plants. And you can see solar, we're getting more energy, but we're not necessarily getting a heck of a lot more energy. And as we know, it doesn't really show up on that peak day. So we need this amount of energy to get through these peak windy days or winter days. Let's talk about how we're investing to actually achieve that. So this is year-over-year changes in terms of our generation capacity, the power plant we've built. So we built a lot of wind and shut down a lot of coal in 2020 and 2021 versus 2020. We got a lot more wind, a lot more solar, shut down more coal. You can see in 2024 and 2025, going into those years, we've built an enormous amount of solar, right? Let's see what we got on our winter days, those hardest days to match everything. So the top is actually the year-over-year change in the total need, that total demand. So as it drops down, it was a less cold year, or a less cold days in the winter. If it goes up, then it was a colder winter. You can see that although we're making massive investments in solar, it's not contributing to that energy that we need on those winter days. So it can be a low-cost source of energy, but it's not hitting that marginal day. I need to have backup power plants, and when those demand is high, increasingly it's gas, although you can see in 2024, our year-over-year change in coal went way up, even though we were shutting down coal plants. You can see we another 10,000 megawatts shut down. So this is a tough situation. And it's not just us. The Europeans see it too. So this is Europe basically gets through the winter in terms of electricity supply through its gas storage. It stores a whole bunch of gas for the winter, and then it uses that to generate electricity through the winter, and as well as for heating. You can see they used a lot more gas this year than they have in the average 5 years. You can actually see that right now there's gas storage is down to 338 terawatt hours, which is a lot lower than where they were at around this time last year, maybe about 200 or 300 terawatt hours. Gas prices have gone up. So this is a cost driver and a challenge and an issue for the Europeans. But let's look at what they've done in terms of investment and what they've gotten out of it. So they're like us. This is basically last winter and this winter, their installed capacity across everything. But let's look at the year over year, because that's what they're building or shutting down. Mostly solar, mostly wind. Shut down some coal, shut down some gas, shut down some oil, right? Let's look at, and that's the gigawatt capacity of plant they've built. Let's look at how they got through the winter for November and December. This is the energy from all those different sources. So they got more out of their nuclear. It was a bad hydro year, so they had less out of there. It was a bad wind year. That was the big driver here. So even though they have lots of wind, it was a bad, and they built more wind this year versus last year. It wasn't windy, so they had to burn a lot more gas. So the investment doesn't necessarily line up with how they fill the gaps or how we fill the gaps on these marginal days. So if you look at the investment, which is not in the wholesale price, it gets captured in that retail price. They invested mostly in solar and less so in wind. In this last winter, they were reliant on nuclear and gas to get them through. And so that mismatch happens everywhere. Let's go back to the US. So this is the US last summer and the summer before that. Again, installed capacity up top. Below that, year over year change. So mostly what we built in the US was solar, wind, and batteries between the two summers. Let's look at the summer of 2024. I'll read the quote from EIA, which is the Energy Information Administration. 9 out of the 10 days with the most US natural gas-fired electricity generation on record occurred last summer. We built a lot of wind and solar, but we needed more gas than we ever did. We didn't build gas. We built wind and solar. To get through the hardest days, we needed a lot more gas. And you can see the year over year of the 2 hardest days in the top right. In the bottom right, we saw the year over year difference in the amount of energy coming out. Wind dropped a lot. It wasn't windy. It was less windy than in 2023. We built a lot more solar, so we got a little bit more out of that. Other went down. Well, other goes down because a lot of the other is battery. So it's a cost. So it reduces how much energy we have in the day. So what we're building doesn't necessarily cover our marginal days. We have risk on those marginal days, and it's a significant driver and concern as we go forward. And now let's flip back to Europe, and let's look at a similar sort of thing on gas generation, but this time on Germany. So in the German context, if you look in the top left, the peak annual electricity from gas was in 2020. On an annual basis, they needed more gas in 2020 than they did in any year since then or before that. If we look on a seasonal basis, it was actually Q1 of 2021 where they had their peak use in gas, right? And you think, okay, because building a lot of solar and wind, it's providing it on a seasonal basis or an annual basis, it reduces my annual or seasonal need for these resources. But remember, we need electricity every minute of every day, so we need to zone in a little bit more. If we look on a monthly basis, we actually see, even though that we don't have an annual peak or a seasonal peak anymore, January 2025 was the highest monthly need for electricity. That in fact impacts our storage levels and things like that. And if we zone in even more and look at the daily need, 10 out of 10 days with the highest daily need for gas to keep the electricity system going in Germany occurred this last winter. Germany, like a number of other regions, is building primarily solar and wind, but we're increasingly reliant on these thermal plants on these marginal days if we don't have the right, if it doesn't happen to be windy. So we have two things that are simultaneously true. With increasing variable generation, we are getting more total annual megawatt hours, which is good because low carbon, and it's driving down carbon intensity of our electricity system. But with increasing variable generation investment, we only marginally reduce the need for capacity. Let's do one more example on that just to drive it home again. And we'll do Germany of 2024, more recent example. We're going to do it the same way we did the other parts of Europe because we have the awesome Energy Charts website to use. So this is their installed capacity. Again, a lot of solar, a lot of wind, fair bit of gas, and some coal still. So this is the mix. We're going to do the heat balance or the heat balance chart. So peak day is in winter, so it's a winter peaker. We already know that solar might not deliver much. 76 gigawatts was the hardest day. Let's add in the 94 or 98 gigawatts of solar. It dropped it by 2. So again, we see that if I have a winter peaking system, I can build a lot of solar, but it might not reduce my need for other power plant. If I add in the wind, it shifted actually into December, dropped it to 66. So we did a 10 megawatt improvement. We actually see negative. So we have more wind and solar than they actually need in Germany, which means Germany exports electricity at a cost. We'll go a little bit on that. But if we do the ratioing, then again, for every 1 gigawatt of installed solar, it only reduced their need for other gigawatts by 0.02. And for every gigawatt of installed solar plus wind, it only reduced the need for other gigawatts by 0.06. So that has a cost associated with it, and that leads to challenges. So if we were to actually look at Germany's and France in terms of their electricity prices, wholesale prices, so it doesn't have everything in it. But if you look at versus demand and wholesale day-ahead prices, which is most of the energy volume that's sold each year, you can see France 2019 or 2015, 2019, 2024, it's gone up, impact to the Ukraine war. But if you look at Germany, it's gone up even more in terms of that 2024. So for that net load to hit prices. And if we also look at where Germany has moved its market with the way it's transitioned, we can look at the cross-border electricity. So when it imports or when it exports, and we can look at the value of electricity at that time. So when 2015 or 2016, Germany still had a lot of nuclear, had a lot less wind and solar, and it tended to import or export at a decent price and import at a low price. And actually it netted basically from sales of electricity about 1.5 billion euros. 2019, it's a little bit less. Fast forward to 2024. It cost them 3.8 billion euros to fill in their electricity system. So what does Germany increasingly do? They do that one thing you should never do in a stock market. They sell low. They actually pay folks to take electricity. So you can see the price at negative euros. That's when they're exporting in the blue cloud here. And then they import at high price. So we have lots of extra electricity in the spring and from solar and wind. So they pay neighbors to take that. And then on those winter days or those summer days when they can't make it, they need to pay top dollar to bring it in. So they went from a 1.5 billion euros from their exports to a cost of 3.8. So that's a differential of 5 billion euros. That doesn't necessarily get into your wholesale costs, but that gets into your retail costs, right? And let's zoom back across the ocean, because Germany is not unique. California has gone down a similar route. So we can look at, we got 2021, 2022, 2023, 2024. This is the day ahead price of electricity times the solar output to get the revenues or costs associated with that generation. So we had about 15 or 16 gigawatts of solar in California in 2021. It had about $1.1 billion of revenue based on electricity prices. Built more, and 2022 was a good year because gas prices were really high. Built more in 2023, and all of a sudden now we're seeing in May the prices are getting a little bit lower. Maybe we have too much solar to necessarily cover everything. Go to 2024, it costs money to have solar in the spring in California now, and that's because of that oversaturation. And you can look at that in the left. So we've got the every hour of the day, because that's always important for electricity. There's the average price in each of the months. So you can see in January, prices are good in California. You get into spring, and we're in negative prices during the daytime hours throughout, on average, March, April, and May. So if you have a solar power plant delivering then, you need to pay someone to take that energy. Those costs eventually wind their ways into retail prices. So the question is, can we achieve decarbonization reliably and affordably? The answer is yes, but we need to be careful about how we're approaching this, right? So you can look at the German example, where they've built a lot of wind and solar, and they have achieved a level of decarbonization. But we did the same here in the US just through coal to gas switching. And we did it at a significantly less cost than the German system did. That's important. Those are useful, important lessons. I know that that burning gas doesn't sound as good as running all on wind and solar, but the data's in. We can't get to 100% wind and solar system. We need to pay attention to how these systems operate over seasons, over hours, and everything, and do an optimized solution. So let's get back to the punchline I gave you at the beginning. We're going to build a lot more wind and solar, so we're going to need to have flexible plants. They're going to age as we look to decarbonize them, so we need to figure out how to manage that, to keep that reliability and to manage affordability. Seasonality is going to become more and more important. It's always been important that we have this big demand in the summer and the big demand in the winter, but as we're building more solar and wind, we need to be cognizant of when they can help and when they don't, and how to manage that successfully. The hours are critically important. Capacity and energy on those marginal days are critically important. And just because I have a gigawatt of something doesn't mean I'm going to have the gigawatt hour when I really, really need it as we continue down that decarbonization pathway. So I'm going to come back to where I started. We need zero emitting load following resources. We desperately need them if we're actually going to fully decarbonize the system. We need to think about how we scale these carefully so that we can control costs while we're doing it. I firmly believe, and we firmly believe here at EPRI, that that decarbonized future is achievable, but it's a ton of work. There are no simple solutions, and it's going to be a fun journey. So I've gone through this whole presentation without mentioning the elephant in the room. This is how it is today, but our world is changing, and it's changing because of AI. The amount of demand growth that is potential to occur from AI, artificial intelligence, is potentially significant change to our electricity system that's going to take everything that I just talked about and make it a heck of a lot harder. But it should be a fun next 25 years, and I think that's about it. I went a little long, Rudy, but hopefully it was worth the journey.
It was worth the journey, Michael. My gosh, you presented this like a novel, mystery story. Oh, all right, Michael, thank you for the presentation. And if you don't mind, why don't you stop sharing so we can see everybody, hopefully.
I'll see if I can figure that out. Just give me a second here.
Perfect. All right, so thank you, Michael. So as I mentioned before in other talks, I like to have the students ask the first set of questions. And I'm sure there'll be a lot of questions from others. So students, please identify yourself, unmute yourself and ask a question. Or if you wish to use the chat box, drop your questions in there. And between Susan and I, we'll sort it out. Okay, students, you got the floor.
Okay. My name is Sajjad Al-Shemari. I'm a student in ESE. Thanks for your presentation. This is very useful and a lot of information we are got it. Just only as I understand from your presentation, the peak load, it's during the winter and summer. If we are making this load by heating cooling system for all building and everywhere, make it less. This will be make it the peak gigawatt will be make it less or not.
Yeah, so efficiency gains are really important and building standards are really important and that can have a significant impact. But more so, I would say in the summer. Because what are we doing for winter? We're actually moving to heat pumps, right? Because that is a more efficient solution. And so what and still insulation and all that sort of stuff can help us there. But if we look at the data that we've seen from the last few winters here in North America, electricity demand is going up faster in the winter than necessarily would be predicted by how cold it was. And we think that a big part of that is the adoption of heat pumps for heating. So it's really critically important to continue to drive on efficiency and continue to drive on better building standards for insulation and things like that. That should have some significant benefit for the summer, but we've got a separate driving force here in the winter as we move towards more electrification of heating systems.
Thanks.
Okay, question for Michael from students. Students?
I put them to sleep, Rudy.
Yeah, I tell you what, okay, we got a whole bunch of questions in the chat box. So let me just go through them. Nick DeMarco, you think both the actual climate and political climate of Europe will slow down their investment into wind and solar?
So I'm not entirely sure. So I think that like Europe's going to go into, if they continue with the current policy on the level of gas storage that they need to refill, it's going to be a very expensive year. And so they may be stepping away from that. If you look at the various regions, Europe's not a uniform spot. They're not all doing the same thing. I think some regions will continue to invest pretty significantly in wind and solar, but you get other regions that are sort of less enthused about that. So regions that have a lot of hydro, if you think of the case of Norway, where it's sometimes importing high costs from Germany or from UK because of the way the market's set up. And they're looking to maybe limit that and maybe not have the same level of interconnection, which is a bad thing for the energy transition. So I don't think it's going to be uniform across that. I think that will continue to be a lot of solar and a lot of wind adoption, especially if the tax incentives remain, which they more or less do in Europe.
Okay. Suzanne has a question. What role do you think interregional transmission might play in optimizing the renewable resources? Also, do you think markets need to be updated to reflect a changing portfolio of resources?
So I think transmission development definitely helps in terms of optimizing the amount of megawatt hours or terawatt hours I get out of the system. But if we look at like those marginal days, they don't necessarily fix everything. So the big one of the big examples was Winter Storm Elliott here in the U.S. And basically, one of the challenges there was none of the regions had any extra electricity to export to anybody else. So TVA was counting on electricity from PJM and it couldn't, and Duke was relying on electricity from another, and it wasn't available. So transmission can help optimize the amount of energy we get out of renewables. Doesn't necessarily solve those hardest days. If you think about the European example, that's the entirety of the Europe, right? Where that 200 gigawatts of solar only reduced the need by 2 gigawatts. Building more transmission doesn't address that issue. It does increase retail rates, though, if you build more transmission. So I don't think it's necessarily a panacea. It is a benefit if you are a renewable generator because you can get more megawatt hours and terawatt hours in the year, but it doesn't necessarily mean that I can get the terawatt hours or megawatt hours when I absolutely need them. So I think that more transmission makes sense, but it won't necessarily solve all issues, and it is a cost.
Question. Let's see. Miguel Gillis. Great presentation and a mystery novel indeed. So good. Somebody else thinks it's a mystery novel. So let me ask a question that's somewhat related to some of the questions that have come up, Michael. So, India and China are also, they're using energy and they're relying on a lot on coal, to be flexible so that they're also increasing renewables. Is there anything in their strategy that you could find fault in and or recommend something that could be more efficient?
Yeah, so I didn't present in detail on what China and India is doing, but we have looked a lot at it. So like China has built out a lot of pump storage. They have less impediment to building that type of infrastructure than you do in some other regions where you don't have necessarily that authoritarian control. So that's been a nice add. They've built an enormous amount of wind and solar. That pump storage is going to help them move it around. But the fact of the matter is, if it's a bad hydro year, then they really are reliant on their thermal assets. And so they're going to continue to have that. So what China is also doing is they are investing a lot in carbon capture and sequestration. They have a lot of large demos developed on that. Actually, I was a supporter of a recent case study that will be coming out from an advisory board to the IEA, talking about some of the case studies in terms of CCS applications and developments, carbon capture and sequestration developments that China is doing to try to decarbonize their coal. But it's going to be a big challenge. India is on a similar journey with a lot of renewable adoption. And so they're reducing that overall need, like that annual development or that annual energy envelope is really important for the global nation, right? Or for the global CO2 envelope. So lots more renewables help achieve that. For us, we use gas to back that up. Maybe we'll have gas with carbon capture and sequestration at some point to back that up. In China and India, it's going to be coal. Hopefully it is coal with CCS at some point. Yeah, everybody's on a journey here, and it's not necessarily a set of simple answers that work for everyone.
Okay. Question for Michael.
Hi, Mike. I have a very quick question. Excellent presentation. I thoroughly enjoyed it. So I'm faculty in economics, and I think a lot of the issues that you were presenting were related to ramping capabilities, right? So how do you incentivize that? And there is mechanisms like capacity markets, or there's other kind of ways in which actually you can ask, like, without being heavy-handed, right? Like, like talking about like more decentralized cases, but talking about PJM or KAIS or any of those. It's how do you link, like, let's say that actually a capacity market is a solution, right? It's always debatable. But how do you link the days in which you may need that capacity with the payment that is going to be happening in the future? Like, what do you think is the best way to like incentivize the right kind of flexibility at the right locations?
Well, that's a tough question. So I think where I'm at, and I'm not a markets person, but I have been watching. I've been trying to learn the markets for the last 10 years. Where I'm at is we definitely need capacity markets, because because everything else is sort of working at the margins. And when I'm thinking about a power plant, I need a surety for the years. And if I don't have a revenue stream, then I'm going to reduce my maintenance. I may not pay for overtime. And I'm going to basically imperil the reliability of that long-lived asset unintentionally. I'm just going to make the optimal choice for this year, but it's not going to be the optimal choice for the long term. So I definitely think capacity markets are hugely important. Now the question is, okay, how do you make sure that if I'm paying for that capacity, I can get it on those marginal hours? Is that a penalty for not showing up? Is it a carrot? I think that what we saw for the PJM had big penalties, right? What those penalties ended up doing in Winter Storm Elliott was they bankrupted a number of assets. So I don't know if it's all achievable with penalties. I think you need a mix of carrots and sticks there. So I think that it's still an open question, right? Because we only have these test cases every 2 or 3 years, right? Where we got a marginal day and the thing's not working, and it's like, did it work out or did it not? But I definitely am of the opinion that we need capacity markets to shore up these plants, and we need to hold those plants accountable for making the right investments so that they are reliable on that marginal day when they're called upon. And some of that can be easily done, right? So you think about like the EOP standard that NERC developed for looking at winterization. So you just audit it, right? I mean, if there's no heat tracing on the plan and things like that, and they don't have a cold weather resilience plan, then I'm pretty sure they're not going to deliver on that cold weather day. So I think, and some people might get mad at me, I think it's a combination of some incentives so you can have the economics there, some regulation. Did I say regulation too loud? I don't want to get fired. Some regulation and oversight to make sure that that is done correctly, and I think we can get there. But it's not simple. It's not easy.
Thank you so much. Yeah, like a great presentation.
Thank you.
Michael, I'm going to go into the chat box again. What is the current state of new generation nuclear in the U.S. and can that be speeded up? Tinku.
Yeah. So we still have a lot of, and here's the thing where regulation may be slowing us down, right? So there's a lot of potential small modular reactor designs. They haven't all gotten regulatory approval. And so that's a challenge. My personal opinion is small modular reactors are likely able to scale. We just need to have some successful projects. So although it's not licensed here yet in the US, there is a small modular reactor currently being built in Ontario, Canada by GE Hitachi, so that they're both reputable OEMs. They've built big things in power gen before. They've built big nuclear before. They're building a small modular reactor at the Darlington nuclear site in Ontario that's supposed to be commercial by 2029. If that comes in near on budget, near on time, that will be a commercially reproducible project that hopefully we've gone through the regulatory hurdles here that it can be licensed, and we'll be able to start building those. But the test case is 2029. They may sell a few more before then, but all those plants will be built a little bit later. So nuclear, I think, has a role, but we need to get some momentum. As far as the large nuclear, The problem there is just the financial challenge, right? If it takes 20 years or 15 years or even 10 years to build it, and it's a 10, 20, or $30 billion investment, that's a huge amount of money that you have to invest, and you're not making any money off of it until the plant starts up, right? And if it takes an extra 2 or 3 years, that can really mess up the financials. So small modular reactors actually are worse economically in terms of economies of scale, but it's a smaller bite. It's a 4-year or 5-year project, and it's not tens of billions of dollars. It's less money. So those seem to be more scalable and doable. Although we do have a lot of regulatory hurdles in getting those designs approved. We got to learn by doing. I think Stan brought that up last time. So we're going to learn from what hopefully gets achieved in Canada, and then hopefully it scales. But it still remains to be seen.
Thank you. And thank you for an excellent presentation. Keep up the good work at EPRI.
Oh, thank you.
All right, here's a question from Richard Mack. Have you seen any data to say whether offshore wind shows less variation by hour and by season than onshore? Could more offshore wind result in a narrower gap between renewables and dispatchables, at least for coastal demand? This may have been noticed in Germany, so.
Yeah, so I think offshore wind definitely has a higher capacity factor, right? So we definitely know that you get more annual energy from that. I have not really dived in terms of looking at that correspondence with when we actually have demand versus offshore wind. I think that's not going to be uniform everywhere, but offshore wind definitely has a higher capacity factor. You can build a bigger turbine out in a better wind channel, so you can get more annual energy on that. The challenge for offshore wind is sort of like nuclear, though. It's a huge investment, right? A lot of infrastructure and a lot of pressure if it takes longer than anticipated to get built out. And I think that's part of the reason that we had a lot of projects get challenged here in the US, because interest rates went up and the financials didn't make as much sense. But offshore wind is definitely scaled a lot in China on the coast and in Europe, and you get a higher capacity factor. Whether it fully bridges that mismatch of demand versus output, it's difficult for me to say. I haven't looked at the data.
Question in the chat box from Pablo Peña. He's a professor at the University of Uruguay, República Uruguay, and they happen to be one of our partners, Lehigh University's partners in this experiment we call COIL. His question: given the rapid growth in electricity demand from AI workloads and the increasing strain on generation capacity, do you think it's science fiction to imagine a scenario where global companies like Meta, Google, or Amazon start balancing their batch AI processing loads across geographically distributed data centers?
Yeah, so I mean, this is already something that EPRI is looking at. So we have a large initiative called DC Flex, trying to understand that and trying to help that. And I think that works well for like the cloud services, or when we talk about AI inference. So when I ask ChatGPT something, or when I ask Claude something, that you can distribute out those loads and manage things like that. But for making a Claude or making the next version of ChatGPT, those are massive data centers that are crunching the internet, and then they're doing transformations, and that's where the really big load development looks to be occurring in terms of centralized. I need a gigawatt of data center or something like that, because I want it real close so I can compute really quickly as I crunch this, and I can try to make it more smart and hopefully do a little bit better than DeepSeek whatever version did. Those ones, that's an open question on how that compute is going to look like. I don't think you can necessarily distribute it. I think that's going to be more of a when it's running those models. So maybe 3 or 4 months when they're running a model to try to refine it and get the next version out. That's going to be a pretty heavy load. But it's really problematic load, right? So there was just a recent case here in PJM or in Virginia where there was grid fluctuations on PJM, and they weren't AI data centers, but there was a series of data centers, a lot of data centers in Virginia, and about 1.5 gigawatts of that disconnected from the grid, went onto backup power. That's a big problem when a bunch of loads disconnects from a grid. It means you have way too much generation. My frequency varies, and that can trip a grid. So these big giant data centers and more data centers, really understanding how they interplay with the grid successfully is a huge problem. NERC's working on it, EPRI's working on it. There will be some solutions like you've put forward, Pablo, but I think it's an active area of research to really understand what that needs to look like and what that can look like for the different types of data centers that will exist.
Yeah, the second part of Pablo's question that I forgot to read. Pablo, would you like to articulate that?
It's clear. We are facing a similar challenge in Uruguay, and as you mentioned, the peak loads it's a challenge in each country, in each power system. So thinking that the whole planet and to balance the load in a whole planet could be an opportunity for this growth in the case of data center. But of course, depending of the process, I suppose the EA model, to train the EA model, you can save a snapshot and just translate part of the information and continue training in other region, but maybe it's not the case. So it's very interesting to follow the EPRI research in this kind of data centers and how to solve this challenge.
Yeah, it's a really exciting, interesting time. A little bit scary, but exciting and interesting as well.
Well, we have time for one question of Michael. Anybody ask a question? Oh, well, thank you again, Michael. This was just a terrific presentation. This withstands, kind of puts it all together really well. And I really appreciate you taking the time. And really, this is a message to everybody else out there. Please follow Mike's postings on LinkedIn. I mean, those are so wonderful. In fact, I had a preview of what he talked about today and seeing some of his past posts. Thank you again. And the next seminar is 2 weeks from now. We'll have a legal firm talking about what could be done to make a energy policy that's much more facing towards climate change issues. So that's on April 7th. And so we'll see you guys in a couple of weeks. And thank you for your attention. Thank you, Michael.
Thank you very much. Thanks, everybody.
Thank you.